Hello, everyone. In this video, we're going to look at example 1 in section 6.2 in our workbook, where we're using integrals to compute volumes. So I just want to put two pieces of this section in our class together so far. So in the beginning of our class, we learned about how to use an integral to compute area under a curve. And essentially, how we did that was added up a bunch of rectangles defined with their height in terms of a given function. Okay, that's point number 1. Point number 2, in the preliminary example, we saw how we can compute a volume by chopping up that volume into chunks and adding up those chunks together. So in example 1, we're going to kind of put these two ideas together and compute a volume by adding up chunks of the volume like we've done in integrals with areas. Okay, so let's go ahead and get started. So example 1 says, find the volume of the solid region generated by rotating the curve y equals sine of x about the x-axis on the interval from 0 to pi. So let's begin by just setting that up. So I'm going to draw the curve y equals sine of x from 0 to pi. I'm going to set up my axes here. And so the sine function goes from 0 to 1 if we're just looking from 0 to pi. And what that curve looks like is a nice hump like this. It's a little bit more symmetric, so I'm just going to try again here. There we go. We'll stick with that. Okay, so there is the shape that we're given, y equals sine of x. And we want to find the volume, but volume of what? Volume of the solid region generated by rotating this curve around the x-axis. So let's try to imagine that. So what that means is we would imagine this x and y axis in 3 dimensions. So it's coming outside of the page now. And we're just going to swing that curve around. And so at each point, we're just going to get a little trace like this. And what ends up happening is down here, we get sort of the reflection of our original curve. And then that shape, that solid shape, kind of protrudes from the paper. We get a shape like this, kind of like a football or a lemon or something of that nature. All right, and so we want to find the volume of this shape. Well, how can we think about this volume? Well, as these image suggests that I just drew here, we can think of these volumes as a bunch of discs. So if we sliced up or took a knife to this lemon and just chop, 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 perpendicularly along the x-axis, we'd end up with these little chunks, like little discs here. So imagine maybe we have, what is this, a beet? It kind of looks like a beet. And we made slices like this, and then what we end up with is a slice, and we actually call them slices. So I'm going to call this my slice. So this is one slice of this volume. But the strategy or method that we're going to use to compute that volume is to add up the volume of each slice. So let's go ahead and look at what a slice actually looks like. So this is a slice of, we'll call it our shape. Or maybe better yet, slice of region, slice of our 3D region. Okay, so what does that look like? Okay, well, we see that it's kind of circular. In fact, it is a circle like this. And that x-axis just goes straight into it like this. So it has a center here, and that center is aligned with the x-axis, or it's like right in the x-axis there. And then what else do we notice about this slice? So it has a little bit of thickness here. But if we're just looking at the front view, then we just see it as a circle. So what we also know about any particular slice is if you give me the x value where that slice is above, then the radius of that slice is just going to be the output of our function. So that radius is going to be sine of x. So if we're drawing that on our slice, we have here the radius is equal to sine of x. So then from this, we can compute what the volume of a slice is. So the volume of slice, well, it's going to be the area of the slice, or the area of the top of the slice here, or the front view of the slice, which would be pi r squared. So r is sine of x squared. But then we have a little thickness here. So this is referring back to the volume of a cylinder. We just have a very short cylinder, and it's just turned into a slice. So then that's a change of x, a little bit of change of x. So the thickness of a slice is change of x. So what we need to do to compute the volume of this entire region here is to add up the volumes of each of these slices. So how would we do that? Well, we can use an integral. So the complete volume would be the integral of what? Well, we're going to compute these slices, or the volume of each slice. So pi times sine of x squared times dx, because we're using an integral. And d of x, that's the integral we're integrating with respect to, or in other words, that's the axis that we're chopping up, little chunks, little dx's. And we're going to look at these slices for what values of x. Well, x is going to start over here at 0 and go all the way to pi. So we're going to go from 0 to pi. All right, not bad. So now we need to just compute to this integral. So I can factor out that constant pi, integral from 0 to pi of sine, and I'm going to rewrite this in the more conventional way, sine squared x dx. What that means is I'm just squaring sine. And now, since we just looked at a couple weeks ago the integral tables, or computing integrals using tables, perhaps this integral is fresh in our brain. But it turns out this is an integral from our table in Formula 63. So we can actually look up how to compute that integral. So we can go ahead and refer back to that integral table. So we see 63 is sine squared u. So we get 1/2 u minus 1/4 sine 2u. So I'm going to go ahead and copy that down. Feel free to get out your integral table so that you can follow along and check my work. So we get pi times, we had 1/2 x in our case, because we're using x for our variable, minus 1/4 sine of 2x. And that's being evaluated at x equals 0 to x equals pi. All right, so now we just plug in here. So we get pi all times 1/2 pi minus 1/4 sine of 2 pi minus, and I'm going to use parentheses, so no negatives, drop, 1/2 times 0 minus 1/4 sine of 2 times 0, which is just 0. Okay, I'm going to erase a little bit here just to give myself some more room. You should make sure you keep all of your notes, though, so you can look back at it. All right. And we see a couple of things cancel. So sine of 2 pi, that's just 0. Sine of 0 is 0. So that really cleans things up. So in the end, we're just going to get pi times 1/2 pi. And we notice 1/2 times 0 is just 0. In fact, that's all we have, pi times 1/2 pi, which is just 1/2 pi squared. And in this case, we're not given units on our axes. So we don't have units to put on this, but this would be a cubic unit. Cubic unit, where a unit is whatever unit we're given. In this case, we're not given a unit, so we can just write 1/2 pi squared as the volume. Awesome. Great work going through this first example. We're going to look at two more examples in this section to help us get more familiar with using this technique to compute volume.